So matrix multiplication verification is what we were doing. So do you want to recall the problem? What was the input? Or 0, 1. And I want to output 1 if AB is equal to C. So AB is mod 2. So multiplication is modulo 2. Okay, so what was the algorithm that we thought can be used? Right? So I think we tried to do this. So there was some mistake in this algorithm, right? One-sided error. So yeah, so now can you try to fix it using randomness? So let's say that this is algorithm A. So A is given as input 3, okay, so this is also A. A. Given as input 3 matrices A, B, C. It has to output either 0 or 1. 1 if AB equal to C and 0 otherwise, right? That's the algorithm we want to design, right? The algorithm also has access to some coins that it can toss whenever it wants. So would it be possible for you to modify this algorithm? Currently there is no randomness in what I have written and it does not solve the problem correctly, right? So there is error in the way it is written. So what can you do? You have to introduce randomness because this algorithm is given some random coins which it should use.
Picking x is random.
Okay, so let's pick x uniformly at random from 0, 1 to the n. So how would you do that? I think we saw this. So n independent coin tosses you will make, right? And whatever is the outcome of the coin toss, you will write it here. What you will get is a vector in 0, 1 to the n. So what is the probability that this vector x is equal to all zeros, for example? Huh? So this notation is okay, right? N zeros. 1 by 2 to the n, right? Not just this, any fix, you fix any bit string here, the probability that x will be exactly that bit string is 1 by 2 to the n, right? Because if you fix a bit string, let's say a1, a2 to an, where each ai is in 0, 1, the probability that x1 will be exactly a1 is half, and the probability that x2 is exactly a2 will be half. These are independent, so you can multiply the probabilities. Is that okay? So every outcome is equally likely. That's what uniformly at random means. No bias. So this is the algorithm. So why is this algorithm correct, or how correct is this algorithm? So the algorithm is clear. The algorithm is going to, the machine is going to toss a coin n times. We will call this an unbiased coin. Okay, so that's what books call it. Meaning that probability that head is equal to probability that it is tail is equal to half. No bias. There are also some biased coins. Most of the times it will return head, only sometimes it will return tails. More sophisticated examples, such coins will be used. But here it is unbiased. Toss a coin, head and tail are equally likely. Okay, so this algorithm has 3 matrices, it has coins, so it's going to first step toss the coin n times, it's going to generate a vector which will be uniformly at random because the coin is unbiased. Okay? And then it will multiply b with x and then a with that vector, c with x and find the difference. If it is 0, it's going to say AB is equal to C, otherwise it's going to say AB is not equal to C. Is the algorithm okay? So can you say how correct it is? I mean, how do you analyze correctness? So you have an algorithm, so we have to analyze 2 things, right? What are the 2 things? We had to design an algorithm, we have designed something. Correctness is something, and what did you say? Soundness is correctness, right? Whether it is sound. Correctness, soundness, I mean, is there an error on which, is there any error? Right? On the right answer it should say yes, on the wrong answer, wrong input it should say no. And? Sorry, I did not hear. Efficiency, runtime, time, space, depends, here we are interested in time, there are algorithms where you may be interested in space, right? Okay. So I'll write complexity analysis instead of runtime. So when I say complexity, it might be time, it might be space. Okay. There is another measure of complexity here, which is randomness. Okay. So how many random coin tosses are you making? Here you are making n tosses. Can you reduce it? Right? This algorithm makes n coin tosses. So randomness is a very important measure because true randomness is very difficult to obtain. We don't have source to generate true randomness. All our rand functions are pseudo random. Right? We have to see what pseudo random is. So randomness is very costly as time. Okay? So this algorithm, what is the time complexity? Order n square. So because we are imitating matrix vector multiplication. Okay? Space is fine, so you can calculate space. It might be order n square. Randomness is n random bits. So now we have to do the correctness analysis. Is it okay? So what should you show for correctness? What he said, soundness and other things. So either the input is a yes instance or it is a no instance, right? There are 2 possibilities. So the first thing we need to show is if AB is equal to C, then AL is the algorithm, right? Should output what? 1 or yes, right? If AB is not equal to C, then ideally in the deterministic case, you would want the algorithm to output no. Right? But here you cannot guarantee that, there is some randomness. So it should almost always output no, right? So with some probability. So I'll have to fill this up, I'll fill. So let's do the first part, then I'll fill the second part. So suppose AB is equal to C. Okay, so the input instance is A, B, C, 3 matrices which are 0, 1 such that the product is actually correct. So how will the algorithm behave? So it will pick an X, right? And it has to verify. So will it be correct? Will it be wrong? So for every X we saw if AB is equal to C, this property is true, right? No matter what X it is, whether you choose it random or arbitrary, or you can do your favorite things there, right? So then the probability that algorithm outputs yes is what? 1. So what is this probability over? So there is probability means that there is some random experiment going on, right? Otherwise this term won't make sense. What is the randomness? Where is the randomness coming from? x, right? So this probability they say is over the random coin tosses of. So where is the probability coming from? That's what you need to write. So most books don't write it, but some good books will actually write. So under probability, under expectation, there is usually a small thing there that's written. Right? So where is this coming from? Sometimes there are multiple random variables. You may take expectation over one of them. So here the algorithm is making many coin tosses. Subject to those coin tosses, the probability that the algorithm outputs yes is 1. So here the algorithm is always correct if AB is equal to C. But now when AB is not equal to C, there will be a problem. Okay. So what if AB is not equal to C? What can we say? So is that okay? I mean one direction. Otherwise we can do it again. It's not true. Is it fine? Okay, so what if AB is not equal to C? Hey, so if this is not clear, you should ask, because the next thing is going to be much more complicated. Is this okay? I mean, this one should be fine. Even if it's not okay. So what if AB is not equal to C? What can you say?
Probability depends on number of x.
Correct. So there is this whole world of x's which are possible. So totally there are 2 to the n possible choices for this x. Some of them may be good, some of them may be bad. So what is bad? First we have to define that. But if the bad x's are very small, then when you pick something at random, it is very unlikely that you will hit the bad things. Right? So if there is a box that has all blue balls, but only 2 of them are red, right? You draw uniformly at random, it's very unlikely that only those 2 will come. There is a non-trivial probability with which it can come, but it is not high. Right? It's just 2 of the 1000 balls which can be blue or red. Okay. So what is bad x we need to define. So suppose AB is not equal to C, right? What would be a bad x? All zeros is one of them. What else can be? That's right, all zeros. Because if you substitute all zeros, both will be 0. Then the algorithm will give a wrong answer. ABX minus CX is equal to 0. So all those x's that force the algorithm to be incorrect, those are your bad x's. Is that okay? All zeros is one of them. There can be many of them. In fact, all of them that are solutions to this linear equation are bad choices. Right? So now I want to estimate how many of them can there be. Okay. So let me define something. It's what he's saying, but I have to give things a name so that it's easy. So the bad case is when AB is not equal to C, but ABX minus CX is equal to 0. Right? 0 vector. That's the bad case. Okay. So let me give it. So what do we want to analyze? Now I have to say that this will not happen very often. So I have to say that the probability that ABX minus CX is 0, right, is small. Assuming that AB is not equal to C. Right? If I pick an x uniformly at random. So the probability that x is chosen uniformly at random from 0, 1 to the n, the probability that these two things actually unluckily become 0 is very small. In small I have to quantify. That's where the algorithm is forced to err. But every other place will be fine.
Isn't it supposed to be 0?
Sorry?
Isn't it supposed to be 0? Because AB is not equal to C, so we should get 0. Right?
No, why is it? So AB might not be equal to C. Okay, so you want to write D for AB minus C?
0 complement, what do you mean?
Oh no, it's not 0 complement, it says 0 vector. Okay. So what did you ask? So maybe we'll come back. Okay, so when does the algorithm error? If the input ABC is such that AB is equal to C, the algorithm is not going to make a mistake, right? So the only possibility is AB is not equal to C, and we picked a wrong X. So in the example in the morning, I don't know if you attended, we had two 2x2 matrices, AB and a matrix C, such that AB was not equal to C. But when you pick X equal to all ones vector, so this is vector notation, okay, so if you are not comfortable, then it's 1, 1. Somehow unluckily ABX was equal to CX, right? But amongst the 4 possible vectors here, one of them is bad. And if you pick one uniformly at random, it's lower, right? So the larger the vectors, there are some bad ones, there are some good ones. So the bad case is when AB is not equal to C, but somehow magically this difference became 0 vector. That's what we want to analyze for how many such x's. So the whole family of x's is these, 2 to the n many. Some of them are bad candidates, right? Some of them are good candidates. So what is a good candidate? Whenever AB is not equal to C, ABX should not be equal to CX. Right? Then your algorithm will output the right answer. Is that okay? So this bad and good distinction. If it's not, you should take some time, stare at the board and figure out. So this is what we want to show. Yeah, it might get slightly messed up, so you should be confident that you have understood so far. Is that okay? So I want to exactly estimate, there are these 2 to the n possible x's. How many bad x's are there? How many good x's are there? If I can measure that and say, okay, look, so many good x's are there. So if you put your hand inside this box and take one x, it is very likely that it will be good. If the fraction of good x's as compared to the bad x's is large, then it is okay. Okay, so one general question before that. Suppose I have a randomized algorithm for this. ABC, and I want to output the correct answer with probability half. Can I do that? I want you to design an algorithm that given an input ABC should decide correctly with probability half. It can go wrong with probability half. What will you do? This is a randomized algorithm, it has a coin. So you can toss a coin. This can be any algorithm. For example, satisfiability. Suppose I am giving you a formula and I want to test whether it is satisfiable or not. I want you to design an algorithm. You don't have to design an algorithm that is always correct. With probability half, it should be correct. You have a coin. You also have a formula. You have a coin, what will you do? Toss the coin, right? So if it turns up head, say satisfiable. If it turns up tail, say not satisfiable. Don't look at the formula. The formula is some piece which is given to you. So what is the probability that this will be correct? Half, right? So half is not the right target. If you want to get an algorithm that succeeds with probability half, don't look at the input. You have a coin, toss the coin. For decision problems, there are only 2 outcomes, right? Yes, no. So if you can toss the coin many more times, you should get better answers. So now you can ask for satisfiability. I have to find a Boolean assignment. Maybe I can toss the coin n times. And based on the outcome, I will say set 0, set 1. Is this a good algorithm? So half is not the right answer. For randomized algorithms, if you want a good randomized algorithm, you have to succeed with probability strictly greater than half. Half you can always do. You have a coin. So every decision problem has a randomized algorithm that succeeds with probability exactly half. Don't look at the algorithm. Don't even ask what is the algorithm. What is the problem I want to solve? Nothing. Just toss the coin and say yes. So the probability of success should be greater than half. That is what the challenge is. So equal to half is easy. To get from there to non-trivial, right? For example, 0.6. That's what is hard. So these things, whatever we are saying, small meaning it should be strictly less than half. So that probability that the algorithm is right is strictly greater than half. Okay, so this is, if you don't understand the math, it's the probability that the algorithm errs on input. The probability that the algorithm is wrong is smaller than half. That's what we want to argue. I have not argued yet. So a randomized algorithm with probability half is easy to see. Okay, so there is one more thing which is a side result, which also you may have seen in school. Okay, so suppose I have an algorithm. I have a decision problem. Okay, this can be any problem. You can take whatever problem you have seen in this course. And let's say you have an algorithm, and this algorithm is randomized. So there is a probability with which it will be correct. Right? Randomized algorithms, it cannot always be correct. So let's say the probability that the algorithm is correct or correctly solves this problem, so let's say 0.6, some non-trivial number that's greater than half. Now ideally I want to get 1, but I don't know how to get 1. Right? If it's a deterministic algorithm, I'll get 1 here. But currently I have some algorithm I have designed, it's only 0.6. Is there a way to get from 0.6 to 0.7? So I am improving the probability of success. Is there a way to do it? Have you seen this at school? So can you repeat this algorithm? Right? So here maybe you took 1x, you checked. Right? You were unlucky, somehow the algorithm outputted the wrong answer. Run it one more time. It will pick another y. Right? Maybe that time also it was incorrect. But if you run it 100 times, it is very unlikely that all the 100 occurrences will be incorrect. Right? At least in most of them, it will pick the good x. Right? So the probability that if you run it 100 times, all the 100 x's are bad is much lower. And there is a way to bound it, because all these trials are independent. Right? So first trial, the probability that it is correct is 0.6. So the probability that is incorrect is 0.4. Right? I run the same algorithm twice. What is the probability that the first time it is incorrect and the second time it's incorrect? 0.4 into 0.4, because these are independent runs. If you run it one more time, then the probability that all the 3 things say no, right, is 1.4 to the 3. So if you run this algorithm r times, you can get non-trivial probability with which it will be correct, right, like 0.4 to the power r. Of course, you will have to run it many, so the more number of times you run, the closer you will get. But the problem is you will have to invest more time. Right? You are running it again and again, sequentially, it's not parallel. Right? So first there is an n square, then there is another n square time, another n square time. And the number of random bits that you are using, that's also going to increase. So the more time you get, the closer and closer you can get. Of course, you cannot get to 1, right? But you can improve your probability much better than what you started off with. I mean 0.4 to the 100 is much better than 0.4. Right? This is the probability that it is incorrect. So 0.4 to the r is much larger, much smaller than 0.4. So it gets better and better. The probability of error goes down as you repeat the algorithm. So this is called boosting success probability. So this is something you have seen. It uses the fact that these are independent, so their probabilities can be multiplied. So you have an algorithm which is good, which is randomized. You repeat the algorithm many times and take the majority answer for decision problems.
0.6 is also getting multiplied at time.
Yeah, you can, correct. So you can either analyze the probability that it is correct or the probability that it is incorrect.
0.6
No, I did not get why.
0.6 into 0.6, if we repeat it 2 times, it will be 0.3 something. The 0.6 probability of success or increasing.
So success is when the algorithm reports the right answer. Right? It's 1 minus the probability that it is incorrect. So if this goes down, 1 minus will increase. You are saying there is some problem in the argument?
0.4.
So that's the probability that the algorithm is incorrect. right? So you repeat it so many times, I don't know, maybe 1000 times. This will be smaller compared to 0.4. So the probability that it will be correct will be closer to 1.
If you do the same argument on the opposite side,
Well, you can. Why? What is the problem?
0.6 to the power 1.
No, so here I am taking the majority, right?
Now you don't know if there is success or not.
So here it is one-sided, that's why I analyze the probability that it is incorrect.
No, at each trial, the algorithm giving correct answer is 0.6 by.
So let's say greater than half, okay. 0.6 was just.
What they're
Like,
asking
why
is
we
that
can't multiply?
every time you multiply 0.6, you get lesser and lesser.
No, it is not become. You are correct, but it's not like.
No, I did not get. There is something incorrect.
It's correct. Independent trials.
No, so what went I should understand.
No,
Why did you multiply the
trying to say
probabilities?
that the 0.4 power R you are trying to get when the algorithm is incorrect.
Correct.
Now, if I think algorithm is correct, probability is 0.6. For n trials, it will become 0.6 power n. Algorithm is correct. So 0.6 power n is obviously less than 0.6. So algorithm being correct is also getting reduced.
No, that's not how you analyze, right?
Yeah,
No, so you analyze the probability that it is incorrect. The probability that is incorrect goes down. Probability that's correct will not go down. You're boosting the probability, right? So you should get closer and closer. So you analyze this and take 1 minus this. So you will get closer to 1. Okay. So maybe we can just analyze the probability that is incorrect. Okay, so maybe I will take that offline. Okay, so there was some, maybe I did not describe it correctly. Okay, so this is something we have to do. He asked me to give a name, so I don't know. So let's call this the difference matrix. So what do we know? We know that AB is not equal to C. That's the case we are in. When AB is equal to C, the algorithm is always correct. So AB minus C is non-zero. So D is a non-zero matrix. I think this notation is fine. Okay, it's not a vector, it's a matrix, not the zero. So what does it mean? There is one entry that is non-zero, at least one. There can be many. So let me assume that the ijth entry is non-zero. So your ith row. At least one of them is non-zero. Let's say this is non-zero. So can you figure out what we are trying to do? So we are trying to count the number of good x's and the bad x's. So there may be bad x's. So how do you think we should count? Some exercise on counting that you have seen. So let me call this Dij. Okay, so this entry is that okay? Like some entry is non-zero. So I'm going to consider a vector V whose ith entry is 1, every other entry is 0. This is one vector. I'm fixing the vector. So it's a deterministic vector. What that vector is depends on D. You look at where it is non-zero and then put a 1 there. Is that okay? So maybe you can assume until this everything was 0. So you put a 1 here. So this is the matrix D. This is the vector V. So what can you say about the vector? So the product is a vector. This is n cross n, this is n cross 1. So what can you say about the entries of this vector? So there are some entries here, there are some. In particular, what can you say about the ith entry? Why is it 1? Why is it 1? Okay, it's a 0 1 matrix. Okay, so let me put Dij. It's non-zero. Here it is 1. Okay. So do you recall something from Vaibhav's talk? I don't know if you do, but so this vector is non-zero, at least that's clear, right? So this is a non-zero vector, the ith location is non-zero. Maybe there are other locations that are non-zero, but I don't care. Okay. Okay. So let's record something. So if I pick an R, I don't know if I should pick uniformly at random. So let's take, we are taking an R, okay. So R is what is chosen here. So we gave it a name, X is it, okay. X. X is what the algorithm chose. It may or may not be good, I don't know. But what can we say about X plus V? Okay, so V is this vector. Okay. And X is the vector the algorithm chose. Okay. V is a fixed vector. V depends on D. Okay. So what can we say about X plus V? Or what can we say about D of X prime? So X prime is this vector I just obtained by adding X to V. Okay, X is some vector the algorithm has chosen, V is the vector you designed. It's a fixed vector. Just add them up and give it a name which is X prime. You don't have to give it a name also, but. So what is this? This is D times X plus D times V. So somehow the algorithm incorrectly chose an X, let's say. So then what is a bad X for us? So a bad X is D times X is 0. D is non-zero, but somehow your D times X is 0, right? That's what a bad X is. So bad X. So you say a vector X is bad if D is non-zero, but D times X is 0. That's when your algorithm is going to output the wrong answer. Is that okay? So if I take now D times X prime, that's D times X plus D times V. So D times X was 0, and unfortunately your X was bad. But D times V is some non-zero vector. Non-zero. That's how I chose V. Right? D times V was this vector, it's not the 0 vector. So D times X prime is not the 0 vector, which means X prime is good. Is that okay? So maybe you are completely lost, then I don't know how to get back, but if you are following until this, then you should figure out. So X was a particularly bad choice by the algorithm. What does that mean? It means that the input instance was AB not equal to C, meaning D not non-zero, but somehow when you multiplied it with X, it became 0, like the bad example that we had, or X was 1 1. Okay, that's a bad choice of X in our example. Now what this says is for every bad choice of X, there is another vector X prime that is good. Is that okay? So you have bad X's, you have a bad X, there is another good X that you can get, good X prime that you can get. Can two bad X's map to the same good X? Suppose there is a bad X and a bad Y. Suppose to a good Y prime. Can X prime be equal to Y prime? So there are two bad things here. This is X, this is Y. X we know maps to some X prime, meaning from X you can get a good X prime. From Y also you can get a good Y prime. Can it be that these two things are the same? So if it is, what does it mean? It means that, okay, so can X prime be equal to Y prime? If X prime is equal to Y prime, what can you say? X prime is X plus V and Y prime is Y plus V. This implies that X is equal to Y, right? So this means that this map is, sorry, 1 to 1, right? So for every bad X, there is another good X, and there is exactly one good X for every bad X. So what does that mean? At least as many good X's as there are bad X's, right? Otherwise this cannot happen. Okay. So that is something we should write. Maybe I'll write here. Yeah, if you're seeing it for the first time, it will take some time to figure out how someone came up with this algorithm. But there was nothing particularly great about this algorithm, okay. So what it does is it just uses the fact that if AB is equal to C, then no matter what vector you multiply on the right, it will be equal. If AB is not equal to C and you pick a vector uniformly at random, it is very unlikely that it will become equal to 0.
When you are doing x plus b,
Huh.
how are we sure that it's in that circle region?
Which region?
0 to 1 and it can come out, right?
Okay, so I should do mod 2 maybe. Yeah. So if you assume 0, 1, every operation is mod 2. But all this whole algorithm will work without any binary things. If I replace everything with any real number also, it will work. I just put in 0, 1 so that I can write. So in fact, you need not even say that Dij should be 1. Dij can be any non-zero number. But
Finding V.
so I'm not finding V. So this is only in the analysis. This is the V. The algorithm does not find V. So if you step back, this is not part of the algorithm. This is part of the analysis.
Yeah, because if we have AB minus C matrix, then there is no need of algorithm at all.
Correct. So we are not. So the algorithm is not going to compute AB minus C. Then it means it's computing AB. I don't want to do matrix multiplication. So the point is to verify matrix multiplication, you don't have to do matrix multiplication. So this is only in the analysis. So the algorithm does not do anything about D. It does not find difference. It does not compute AB at all. It just multiplies B with this vector, A with the resulting vector, C with it does 3 matrix vector multiplications. Right? So this whole thing is analysis. So this distinction you should be able to make. So the algorithm does not do anything that is not written in these steps. So everything else that we did is a part of analysis. I mean, you design an algorithm even when you want to work on some problem. You have to design an algorithm, that's the first step. For that you should have some intuition. Once you design the algorithm, you have to prove that it is correct. Right? You cannot just say here is the algorithm, I think it will solve this problem. Right? So you have to mathematically argue that it will. The argument that it will, here I have some freedom, I can fix the V. Right? Okay, so what did we say? We said that, so this intuitively says that the number of good x's is at least the number of bad x's. Maybe much larger also. So at least half of them are good. Okay, so now I hope it's okay. So now what is the probability that ABX minus CX is non-zero? So this is the probability that X is good, right? So this is at least half. Is that okay? So this is the probability that the algorithm is correct. So then the probability that the algorithm is incorrect is less than half, strictly less than half. So with good probability, you have succeeded. So there are some things to note. Maybe you should take 2 minutes to step back and see what we have done, and then I'll see. Yeah, so the takeaway is that ideally in the deterministic setting, you would have ended up multiplying matrices. Here you have not multiplied matrices. But the problem is, in the deterministic setting, you would have always been correct. Here you are incorrect with some probability. But if that probability is still small, it is okay. So there are problems for which you do not know any deterministic algorithm that is efficient. I mean, here you knew at least an n cubed algorithm, right? So the next example that we will see is an algorithm that is for a problem that is NP complete. So you cannot hope to find polynomial time algorithms, but you can find a randomized algorithm that is almost always correct. Then it is good. Randomized algorithms for hard problems. And if you run the same input several times on this algorithm, it will give different answers. Whereas in the deterministic setting, that's never going to happen. Right? So that's the real distinction between randomized algorithms and deterministic algorithms. Same input, same algorithm, you will get different answers. Because the coin tosses in every step, right? They may be different. The outcome of the coin toss. Whereas in a deterministic algorithm, the path that the algorithm takes is determined by the input. So maybe now we can, so this algorithm had a peculiar property. It says one-sided error. So in the yes case, it's always going to say yes. But in the no case also, it may incorrectly say yes. So these algorithms are well studied. There are also two-sided errors. I mean, in both sides there can be an error. Okay, so this is one. I have 15 minutes, so maybe I will do. Okay, so this algorithm is called free balance matrix. That's the name of the algorithm. It's by free balance. I don't know from when. 70s. Yeah. Okay. So I'll erase this. Okay. So, huh. So no two things map to the same thing, right? Yeah, you can write it either way. So algorithm is incorrect. You can make it, you want to make that greater than half, strictly greater than half? Yeah, it can be made greater than half. So how many bads and how many goods I did not exactly count, right? If the number of goods is strictly greater than the number of bads, then the number of choices will. So one of them should be, so there is always this thing, right? It is one minus the other. So if this is strictly less than half, then the correct thing would be 1 minus this quantity. So you analyze one of them, some of them will choose to analyze that. Okay, so this next problem, maybe 15 minutes. So have you heard of this problem? I don't know, did Venkatesh mention? He didn't. Okay, so G is a graph. Have you heard of cut in graphs? I don't know. Yes, no? Okay. So a cut is a set of vertices, or maybe, yeah, I can even define it as set of edges. Okay, I'll define it as set of vertices. Okay. Yeah. So it's a set of edges. So maybe I should give an example, then it's easier. So you have a graph here, in some graph that I've drawn. So I'm going to take two bags. I'm going to put some vertices in this bag and some vertices in this bag, and I'm going to count the number of edges that go across. So this usually you may see in networks, right? If there are many edges that go across, then there is high fault tolerance, kind of, right? Even if one path is not okay, then there are other paths that help flows. Or road networks where there are, ideally there should be many roads between ports. Even if one of them fail, then there are many, and so on. Yeah, I'm not going to motivate, but I'm going to put these 5 vertices into 2 bags such that the number of edges between S and, okay, S is a bad choice, between C and B minus C is maximized. Okay. So can you try to put in? Well, you can just put 1 here and everything else there. Then the number of across edges will be only 2, right? Or I can put 1 and 5 in C and this in B minus C. Then the number of across edges will be 3. Is that okay? Are there better things?
At least it should be of maximum value.
But can you get,
Please.
at least he said. So can you do something else? I don't know. Okay, I don't know one. I have something else, so maybe I will try. Okay, I should not draw on this. Okay, I don't know. Let's see. How many cross edges are there? So one was 1 and 3. The other side is 2, 4, 5. So how many edges are there? 1 to 2, 1 to 5, 3 to 2.
3 to 4.
That's all, right? It's 4. Is that okay? So this is the maximum that you can do. So suppose you are actually given a graph, right? And what I want to do now is sort of partition the vertices into two sets V1 and V2 such that the number of edges between V1 and V2 is maximized. Is that okay? That is incorrect, is it? This is 2, 4, 5. There can be many other options, okay, that achieve the same four edges. This is just one example. Okay, so formal definition would be, it's this set of edges such that there exists V1, V2, which is a partition of V, and S for all U, V in S, U is in V1 and V is in V2. Yeah. This means disjoint union. It is a partition. So you have to partition the vertices into two sets such that the number of edges between these two sets is maximized. So you may have seen, like some graphs have something like this. Generally, right? So these edges are very delicate, like very important, it's bridge. So if that collapses, the graph will be disconnected. So these are used in flow. These kinds of problems are studied in flows usually or networks. Is it okay? There's some problem with the example? Example is clear, right? There are many ways to partition. So if I ask you, give you a graph and ask you to find this. So I want to find a set of edges, right, that are maximized. Or I have to find a partition of the vertex set. So I have to find a partition of the vertex set is easier to describe, right? Such that the number of edges is maximized. So one partition is 1 and everything else, but that had only 3 outgoing edges. So then you may say, okay, put 1 and 2 on one side and the rest on the other side, and so on, right? You can try. So how many possibilities are there? How will you try? Why is it 2 power n? Okay, so you are taking S, you are saying all possible, S can be one of the possible subsets of 1 to n, right? And then you take, okay, S, did I give S? I should give C. And take V minus C, compute the number of edges for each of these cases, whichever is the maximum, choose that. Is that okay? That's a brute force algorithm. You are trying everything, trying to put 1, then trying to put 1, 2 on one side, 1, 3 on one side, and so on. But that is not an efficient algorithm. So this, what kind of a problem is this? It's an optimization problem, right? You are trying to maximize some quantity. So this problem is NP complete. I am not going to give a proof. When I mean this problem is NP complete, I mean a decision version. The NP is a class of decision problems, so I cannot talk about optimization. Is the maximum cut at least this much? If you phrase the problem like that, then it is NP complete. So you cannot expect polynomial time algorithms for this. So what do you try? Sorry? Sorry? What did you say? Well, it is NP complete. You can try a greedy approach, but it cannot be done in polynomial time unless P equal to NP. You can try any approach, not necessarily greedy, dynamic, anything you can try. But it is unlikely to be in polynomial time unless P equal to NP, right? Because the problem is NP complete. So what else should you try? So someone said randomized, someone said approximation. So what is a randomized algorithm here? Randomized, I thought for decision it made sense. So by the way, how many of you have seen approximation algorithms? Okay. So the maximum seems difficult to get hold of that number, right? Because it's not because it's NP complete. There are so many options you have to try. So what is the possibility? So what is the maximum value that you can actually get? As many as the number of edges. You want to maximize that set of edges, right? So if m is the number of edges, the optimum value is actually at most m. Right? That's the maximum you can aim for. Maybe you cannot find a partition like this that has the right number of edges, but it is almost there, like not too bad. So that is what an approximation algorithm does. You may not be able to find the right optimum, but you can get somewhat closer to the optimum. So if the actual maximum number of edges in the partition is, let's say, k, if you can get to k by 2, a partition where k by 2 are there, edges are there in the middle, then it is fine. I mean, finding the right answer seems hard, so you should be happy with some approximate answer. And the approximate should not be very bad. Right? I can always find an algorithm that has one edge in the cut. Right? In fact, even the maximum degree can be achieved easily. Put the vertex with maximum degree in this set. Put everything else on the other side. Right? So this has degree B, degree D, let's say. Put the maximum degree vertex here. That's the greedy thing that he was trying to say. So you can ask this. Put the maximum degree vertex here. Put everything here. Try this. Now can you try to bring in things from here to here in some greedy fashion and then estimate. Right? So that those kinds of algorithms have been studied. So here maybe the degree is the maximum that you will get, but the actual cut can be much larger. There are examples where there is a difference. Okay. So k maybe is the right answer. What I want to show is an algorithm where the maximum cut is at least k by 2. If k is the correct answer, the maximum cut value that I will output, my algorithm will output, is at least k by 2, which is okay. It's only half away. Now you can ask, can I get better here? Can I get k by something that's much closer to k than k by 2? So those things people usually study. So that's the area of approximation algorithms. It is usually done when the problem is NP complete. You don't know how to find the optimum answer. You try to approximate the optimum value. So here it is maximization. So you will say the max is at least. So you want the algorithm output to be at least opt by some alpha. For a minimization problem, what would you say? So if the minimum, I don't know, minimum number of colors, let's say, is 10, that's the actual number of colors, but you don't know how to find a minimum coloring, minimum number of colors, but the actual answer is 10, mine won't be that bad, it will be at most 10 times the correct answer. Then your algorithm is good, right? So for a maximization problem, you want the algorithm's answer to be at least opt by alpha, and for a minimization problem, you want the algorithm's answer to be at most alpha times. So the optimum maybe is 10. I am not that far away from 10, but we will see only maximization. Okay, so quickly I have like 5 minutes. The algorithm is very simple, so you should be able to do it in 5 minutes. Okay. So I am going to write for max cut. So the input is a graph. It has this, and let's say there are n vertices. Okay. So what are you trying to do? You are trying to partition the vertices into v1 and v2 such that the number of edges between them is maximized. So another way to say this is I am trying to find a set, let's say C, such that C and v minus C, the number of edges is maximized. Right? Instead of v1, v2, I am taking C and v minus C because it's a partition. Is that okay? So what should the output be? A set C such that the number of edges between C and v minus C is maximized. is some notation, okay, edges between C and V minus C. Is that okay? I'm doing things a bit quickly, but so now I want to design an algorithm for this problem. The input is a graph, the output is a set C of vertices such that this property holds. And you have a coin. So what can you do? So what are you trying to do? You are trying to find a subset of vertices. So what can you do? So the point is, you have a graph, you don't know what vertices to put inside C, but you have a coin. So for every vertex you can toss the coin. If it lands heads, you put it in C. If it lands tails, you put it in V minus C. So how many coin tosses are there? N, right? And what is the running time of that algorithm? Okay, so what is the algorithm? For every vertex B in B, toss the coin, right? If coin is head, that's all. If it lands up head, put it in C, otherwise don't do anything. It means it's in the other side. So number of coin tosses is N. What is the running time? Order N. I mean, you have to toss the coin N times and you have to do some if else checking, right? So complexity analysis is done, right? Okay. So now what do we have to argue? So I am doing this process, and after this process I will get a C that has some vertices on inside C depending on the outcome of the coin toss. I don't know what the coin toss is. Every time it might be a different thing, right? And there is V minus C. So once you run the algorithm, you have a C and a V minus C. So now I have to estimate the number of edges that go across, right? Is that okay? Yeah, if you're seeing it for the first time, it may take some time, but I hope there is some osmosis. You go back and see. So I'll put size of the cut. It means the size of the edges that go between C and A. So what should I estimate? Should I estimate the size of the cut or what? There is some probability involved. So I cannot say the cut is exactly equal to this. You want to say that this cut size is at least this much. Right? So the actual answer would have been M at most. I want to say at least M by 2 edges will be here. Then it is good. But there is some probability involved. So what do you want to say? So let's write what he is saying. I want to show that cut is at least M by 2. M is the maximum. Okay. Is it this or is it something? Is there some problem? So you run this algorithm once, right? Maybe it will produce a cut. You run this algorithm again, it will produce a different cut. So how can you say that the size of the cut is this much? Expected size of the cut, right? So the size of the cut itself is a random variable. The size of the cut depends on this random experiment that you are doing. Right? Because based on that experiment, C is going to change. Based on C, the number of edges that are going out are going to change. So everything depends on coin toss, right? So you cannot say the size of the cut is at least this. That statement is false. What is the expected size of the cut? That's what we can say, right? Okay, so it's not a hard thing. So can you try and estimate this? So how would you estimate the size of the cut? Let's see. So every edge is either crossing or it is internal to one of these. Right? When it will be crossing, when it will be internal, depends on whether that vertex is pulled into C or not, which depends on the toss. Right? So you don't have handle on that. So you can set up what? Random variables. So you can say an edge is in the cut, right, or XE is 1 if E is in the cut. So when I mean E is in the cut, I mean that it is crossing. Or E is crossing and 0 otherwise. Right? So for every edge I am going to set up this random variable. So it's a 0, 1 random variable. So what is the, so when is it 1? When is it 0? This, can you try and see? So when is an edge E in the cut or in crossing? So let's say this edge E is UV. So either U should be in, okay, cut. So either U is here and V is here, or V is here and U is here. Only then it will contribute 1, right? Is in the cut if and only if U is in C and V is in B minus C, or V is in C. Is that okay? These are the only 2 ways in which it can. So now can you say what is the probability that XE is equal to 1? So it's the probability that this event happens, let's call this E1, or this event happens is E2. Right? This is what you've done in school. So what is the probability that this event happens? First V should be put in C, which means you will toss a coin for V. If it's head, you are going to put it in the cut. So that happens with a probability half. And there is an and here. Okay? And V is not in C, which means you tossed a coin for V and it ended up tail. That's why you didn't put. So that is another half. So why was this multiplied? Because these are independent. Right, I tossed a coin independently for each vertex, so it's okay to multiply, right? Plus there was this other possibility, that's another 1 by 4. So this whole thing is half. Is it visible? Wait. I did one cheating which you didn't spot. So I said probability of E1 union E2 is equal to these 2 things. Is it okay? Okay, it has a name, but anyway, let's continue. Okay, so this is the probability that XC equal to 1. So now we'll do whatever you had all suggested in the first. So now what do we have? We have random variables for each edge. There are m edges, right? One variable for each edge, and each is a 0, 1 random variable. And what is the expected size of the cut? Yeah, so if you're seeing it for the first time, maybe you should take notes and go back home and read, because you have to decipher this step by step. So each of them will contribute 1 to the cut or not, right? That's how you set up the experiment. So this is how you would do. So now what can you do? I know the probability that XC equal to 1. It's a 0, 1 random variable. So what is the expectation of XC? Expectation is same as probability, right? If it's 0, 1. Okay. So now what do you do? So this is XC1 plus XC2 plus, let's say I number. So I have to compute the expectation of a sum. What can I do? Linearity of expectation, right? So this is the same as sum over all expected. Each of them is half, and how many of them are there? M by 2 of them are there. M of them are there, so the expectation is M by 2. So expected size of the cut is M by 2. So what did we do? We did some probability calculation which you never understood, and it is fine. Okay, so if you're seeing it for the first time, it can be difficult because we are not taught this way, right? You are not taught to set up random variables. You are given random variables, you are used to analyzing it, maybe probability, expectation and so on. So what is the takeaway? This is a randomized algorithm, right? And you are asked to find the maximum cut in a graph, and that problem was NP complete. So you do not know how to find a polynomial time algorithm for this. You know that the maximum answer that you can get is n. Okay? So you are trying to approximate the answer because you cannot hope to find the right answer. Now, here is an algorithm that is linear time, and it is randomized, so it may not produce the right cut, but whatever cut it produces is guaranteed to have size at least half the optimum. Okay. So it is a good enough approximation, but the algorithm is randomized. So it's a randomized approximation algorithm for max cut. There are many examples. So for example, if you want to solve SAT, okay, you want to maximize your satisfiability, you can try, maybe toss a coin for all the n variables, substitute it. How bad can it be? Okay. So suppose you have a clause, let's say x1 and x2 and x3, or maybe not x3. So how many possible assignments are there? Okay, it is CNF, right? So this should be OR. A clause is OR. Okay, so let's say CNF or DNF, whichever you are comfortable with. So how many possible assignments are there to this clause? 8 are there. There are 3 variables, so there are 8 assignments. How many assignments falsify this clause? Of the 8 assignments. Why do 7 of them falsify?
Only one is true. 4, 6, 5. It's and.
Oh, it's and. Okay, so I will change. Yeah, okay, let me change. It's okay. So how many of them falsify? I mean, you can assume it to be DNF or CNF. It's a Boolean formula. One of them falsifies, right? So there are 8 assignments of which one of them just falsifies. So if I put a bag with all the 8 assignments and pick an assignment at random, 7/8 of the time it will satisfy. There is only one chance that it will not satisfy. So now you can use this to design a randomized algorithm for satisfiability. But it may not always be correct. So there is a probability with which you will hit that one bad assignment, but it is very unlikely. Right? So as the width of the clauses increase, right, it's very unlikely that all of them are somehow unsatisfied. You correctly chose x1 equal to 0. So if you toss a coin, the probability that this happens is half, x1 equal to 0 and x2 equal to 0 is half and x3. So it's very unlikely that you hit the wrong assignment. So in most cases, randomized algorithms are good. There is some error involved in it. It's not always correct, but it is very efficient. So this is linear time. Just toss a coin. Correct. So this will work under some conditions. Because once one clause is falsified, the whole thing is falsified if it is an AND. That is correct. Right? So what you can ask is, I want to somehow find how many assignments are satisfying. In those kinds of settings, this will work. So max cut, max sat, these are examples for which, so the running time is far improved, right? So there you have an exponential time algorithm, here you have a linear time algorithm. And the probability with which it fails is very small. If that is the case, right, in practice, then you can use this algorithm. Very unlikely, some 1 in 1,000th input it may not be right. You are fine with it. How many times is that input going to occur? It may not even occur. So in most algorithms in practice are randomized. So even for testing whether a given number is prime or not, initially there, I think Vaibhav spoke about it, right? There was an AKS algorithm. So initially there was a randomized algorithm. And then people worked on the randomized algorithm and completely de-randomized it. So de-randomization is an area. Yeah, these are terms you should know. Maybe you want to read up or you don't want to read up. So like P versus NP, there is a P versus BPP question. This is also equally hard, equally challenging, equally interesting. It asks, is every randomized algorithm, can it be de-randomized entirely? Or is randomness any powerful? Yeah, BPP means bounded error probabilistic polynomial time. Error is bounded, the running time is polynomial, but it is probabilistic. So these are important classes, just like you saw search problems, counting problems, for which we don't know efficient algorithms, then you will go for randomized algorithms. Okay, so but to analyze or develop randomized algorithms, you should have some sound understanding of probability theory. Yeah, so you should go back and read stuff. So this is taken from a book called Randomized Algorithms. Introduction to Randomized Algorithms by Rajiv Motwani. Yeah, that's why there are many materials online. So randomness is a useful tool in computing. These are computational problems where randomness helps. When you don't know how to solve the problem exactly, you don't have a choice. You have to live with randomness. Okay, so that is all.